Have you ever felt like math is just a big, long list of rules you have to memorize? But what if I told you it's not about memorizing at all? What if it's actually a language with its own grammar, its own logic, that we can use to describe the world in some really powerful ways? So yeah, let's dive into that.
So let's start with some of the basic grammar of this language. You know, the rules of exponents. For a lot of us, we were just told, hey, this is how it works, just accept it. But these rules, they aren't random at all. They're built on a foundation of perfect, undeniable logic.
And here it is, our first big mystery. What is the deal with this? Why is anything to the power of 0 equal to 1? I mean, it feels totally random, doesn't it? But it's not. There's actually a beautiful, simple proof hiding right in plain sight. To crack this, let's start with a fact that is just 100% true, no debate. You take anything, literally anything, let's call it x to the 5th, and you divide it by itself. What do you get? You always get 1. Always. Simple as that. Okay, but now let's look at that exact same expression, x to the 5th divided by x to the 5th, but through a different lens. This time, we'll use the quotient rule for exponents. You remember that one, right? You just subtract the exponents. So 5 minus 5 gives us x to the power of 0. And this is where it all clicks. We looked at the same thing in two different ways. On one hand, we proved it equals 1. On the other hand, we used a rule that says it equals x to the power of 0. Since they both came from the exact same starting point, they have to be equal to each other. So x to the power of 0 must be 1. It's not some random rule a teacher made up, it's a logical necessity for math to even work.
Okay, so now that we've unlocked that, let's tackle the next mystery. Why does a negative exponent suddenly mean you flip the number and turn it into a fraction? Again, looks weird, but the logic flows directly from what we just figured out.
So check this out. Think about this expression, 5 to the 7th power times 5 to the negative 7th power. The product rule tells us we just add the exponents together. Well, 7 plus negative 7 is 0. That gives us 5 to the power of 0. And hey, we just proved that anything to the power of 0 is 1. So for that whole equation to be true, 5 to the negative 7th has to be the one thing that cancels out 5 to the 7th to equal 1. And what does that? It's reciprocal, 1 over 5 to the 7th. See? It all just snaps perfectly into place.
So we've seen that these rules aren't just arbitrary things to memorize. They're part of a consistent system. But so what? What's the point? Well, this language was invented to describe one of the most powerful forces in the universe, growth.
When you really boil it down, an exponent is just a shortcut for repeated multiplication. And it turns out that's exactly how a ton of things in the real world grow. Think about compound interest or a population of bacteria. They're just multiplying themselves over and over and over again.
And here's how we turn that real-world idea into an actual equation. Let's say a car starts at $50,000. To make it grow by 7%, we multiply by 1.07. If we do that for x number of years, we've just multiplied it by 1.07 x times. The language of exponents is the perfect way to write that down.
Okay, so this is a really powerful way to predict the future. But what happens when we want to ask a different kind of question? And this leads us to a whole new challenge.
You know, it's pretty easy to plug in a number for the years, for x, and see how much money you're going to have. But what if you flip it? What if you know the target amount of money you want, and you need to figure out how much time it's going to take to get there? Suddenly, our unknown variable is stuck up in the exponent. Let's make this super concrete. Let's say you invest $1,600, and it's growing at a pretty nice clip, 6.5% every year. Your goal is to hit $2,000. The big question is, how long is that going to take? So we can set up the equation just like we did before. The final amount, 2,000, equals the starting amount, 1,600, times our growth factor, all raised to the power of t, the time in years we're trying to find. But just look at t. It's trapped. It's stuck up there in the exponent.
And this is the problem, right? Your standard tools of algebra, adding, subtracting, multiplying, dividing, they can't get it down from there. We need a special key, a key that was designed specifically for this kind of lock.
And that key, my friends, is the logarithm. I know, it's a word that scares a lot of people. But if exponents are the language of growth, then logarithms are the tool we use to ask questions about that growth. They're the key. That's it. Seriously, that's all a logarithm is. It looks super intimidating, but its job is actually incredibly simple. Whenever you see a log, it's just asking a question. It's asking, hey, to get this final number, what power did I have to raise my base to? Just look at this. They're two sides of the same coin. The exponential form on the left makes a statement, base b to the power of y equals x. The logarithm on the right just rephrases that as a question. What is the power y that I need to put on base b to get x? It's the exact same relationship, just written a different way.
And here is their secret power. This is the whole point. Just like division undoes multiplication, a logarithm undoes an exponential function as long as they have the same base. They're inverse operations. They are designed to cancel each other out. And this is how we're going to free our variable.
All right, so now that we have our ultimate unlocking tool, let's go back to our investment problem and finally solve it. You're about to see just how elegant this whole thing is.
Okay, let's just walk through this. First thing, we got to get the exponential part by itself. So we divide both sides by 1600. That gives us 1.25. Now, for the magic step, we use our key. We take the natural logarithm of both sides of the equation. Because of a handy rule for logs, this lets us take that exponent t and bring it right down in front as a multiplier. And just like that, t is free. It's no longer an exponent. The last step is just simple algebra. Divide both sides by the log of 1.065 to solve for t.
And when you punch that into a calculator, boom, there's our answer. It's going to take about 3.5 years for that investment to grow from $1,600 to $2,000. We went from a totally stuck variable to a concrete, real-world answer. Pretty cool.
So let's just recap the journey we took here. We started out by seeing that these weird math rules like the zero exponent, they're not random at all. They are part of this beautiful, consistent system. Then we saw how exponents are literally the language we use to talk about growth. And finally, we found the key, logarithms, which is the tool that lets us find the missing pieces of the story, like the when and the how fast.
You know, this whole journey from a simple little rule to solving a real financial problem, it shows you that math isn't just about numbers. It's a language. It's a powerful language for asking questions and finding real answers about the world all around us. Which kind of makes you wonder, right? If this is the language of growth, what other secrets are just sitting out there waiting for us to find the right mathematical language to unlock them?